Hey, good morning, everyone, and let's continue with our topic of mesh current analysis. So let's pick up where we stopped. Okay, just as a brief recap, mesh current analysis is a similar technique to node voltage analysis. In node voltage, in both techniques, we wish to write equations for the unknown variables so we can solve for the voltages and currents in the circuit. In node voltage analysis, we apply KCL to write our equations. In mesh current analysis, we write KVL, or we use KVL to write our equations. In mesh current, since we are applying KVL, meaning we're summing up the voltages in those resistors in the branches of our circuit. Okay, and to do so, we make some assumptions. We assume that there is a mesh current flowing through each mesh, and we pick a direction for those mesh currents. And to reiterate the important point, a mesh current is not real. It's completely hypothetical. It does not exist in real life. It is theoretical only for the purposes of theoretical analysis. So keep that in mind. It is not real. It is purely hypothetical. It does not exist. It does not have a physical basis in real life. Mesh current, the only purpose for a mesh current is so we can write and assign voltages for each of the resistors in that circuit. And that's it. Okay, branch currents that we talked about in node voltage analysis, those are real, but mesh currents are not. So we looked at mesh 1, where I pointed out that in mesh 1, we have two resistors, and both of those resistors are shared branches, meaning that resistor is shared between more than one mesh, two meshes in that. It's shared, it's only going to be shared between two meshes, cannot be more than two, physically impossible. So R3 is shared between 1 and 2, and R2 is shared between mesh 1 and 3. And so the hypothetical currents, I1 and I2, are flowing through R3, and I3 and I1 are flowing through R2. Then from those assumptions, we can say that there are two voltage drops for both resistors, which again cannot be physically true, does not have a physical basis in real life, cannot have two voltage drops across the same component, right? Again, this is just for analysis. That's it. Once we have the mesh currents, then we have the voltage drops, and then we apply KVL. That was the next step. So we applied KVL, and we obtained this expression. Now, when I teach, I point out that we have two different voltages for the resistor, but that's only for explanation purposes. Okay, you do not have to write this out if you don't want to, but then you better have confidence in yourself that you're adept at writing out the correct equation. The only reason I write this out, which is plus VR2 and minus VR2, and then plus VR3 and minus VR3, is to explain to students when we first, write down the equations. If you look through a textbook, or if you take another professor's class, more likely than not, they will not have this. They will not have this step. Okay, anyway. So two mesh currents flowing through both resistors, both of them cause voltage drops. And because of the assumed direction of our mesh current, which is I2, I1, and I3, the voltage drops are in opposite direction. Similar to node voltage analysis, The polarity of the voltage depends on the assumed direction of the branch current. It's the exact same thing here. The polarity of this voltage depends on the assumed direction of our mesh current. It does not affect our analysis at all, in the sense that it is not an error. If the answer ends up being negative, it is not an error. Let's take a 10-second pause while you think over that, and let me know if you have any questions.
This is saying that VA is 0.
VA is 0.
Well, if it's plus minus VR2 or plus minus VR2.
No. It's those are two. Actually, I should note down. This VR2 is due to the current I1. And this VR2, the second one, is due to the current I3. That's an excellent point you made. Because if it's plus VR2 and minus VR2, should it just not be 0? So the notation, okay, the notations are different. VR2 due to I1 and VR2 due to I3. Similarly, this VR3 is due to I1 and this VR3 is due to I2. Okay, does that make more sense, everyone? Okay, good catch. So again, those are just notations. And as I said, typically, if I'm solving problems, I would not do this step, right? We would simply write down the current directions and the voltages based on the assumed directions. So then you can see how I added up the voltages. Okay. VR2 due to I1, I apply Ohm's law, V equals IR. Voltage is the product of the current and the resistor. Okay. So in in resistor R2, the voltage again is due to the two mesh currents, I1 and I3. And so I have two voltage drops. The first one is I1 R2. The second one is I3 R2. That's the first one. That's the second one. And the reason it is plus and minus is simply because I chose the current going in the opposite direction. All three of them are clockwise, but if you choose the same clockwise direction for all three currents, your branch currents, one is going up, the other one's going down, or basically they're going in the opposite direction. There's no other possibility. Elaborating on that point, it does not matter what your chosen direction is, as long as you're consistent within the problem, meaning you do not change your assumptions halfway through your analysis, your answer will always end up being right. Okay. So as practice, I always tell students, it is not possible for me to show all the different approaches, all the different currents, current direction, and solve it in class. So I show with the assumed direction here. I would strongly recommend that students go home and choose different directions for those different mesh currents, and then write out those equations, KVL equations, based on those directions. You should end up with those exact same equations, or slightly different because of plus and minus signs. And the reason is, whatever direction we choose for mesh 1, we will choose the same for mesh 2 and mesh 3. I1, I2, and I3 directions do not change for your entire analysis. All right, 10-second pause. Let me know if you have any questions. Any questions? Okay. Then moving on. Mesh 2 is, let's see. This is R3, R4, and VB. My I2 is flowing in the opposite direction. I2 and I1. There's also the matter of the direction of KVL. Remember, when you sum up the voltages, you're going around a loop. So you can choose to go clockwise, you can choose to go counterclockwise, and that also affects the sign of your equation, of your variables. So in this case, again, I'm applying KVL in the clockwise direction, as always. And when I do that, KVL in the clockwise direction, what do I get? I get VR3, say plus VR3 minus VR3, because it causes a voltage drop in these directions. And this would be plus and minus. So plus VR3 minus VR3 plus VB plus VR4 is equal to 0. The first VR3 is due to the current I2. The second one is due to I1. So I'm adding up or summing up the voltages also in a clockwise direction. And that's why I have plus VR3 and minus VR3. If I chose to add up the voltages in a counterclockwise direction, then I would have minus VR3 due to I2 and plus VR3 due to I1. Does that make sense? Right? Does not matter which direction you choose to add up your voltages in the KVL. Everything ends up being correct. And then if I apply Ohm's law, I2 minus I1 times R3 plus VB plus VR4 equals 0. If both my currents were going in the exact same direction, it would be I1 plus I2 and not I1 minus I2 or I2 minus I1. Does everyone see that? Yes.
Would you also want to put VR4 in terms of I2 and R4 on the plot?
Oh, yes. Thanks. Monday morning blues. I2 times R4, which was the point of analysis. We want to express each voltage drop across each resistor. So I2 times R4. Does that make sense? Okay, then mesh one. In mesh one actually has another shared resistor. So
Mesh three.
no. Oh yeah, mesh three. VB R1 and R2 and I3. So this is R1. I'm gonna write R2 far away here. And there's also another current. So this is I3. And then I also have I1 flowing in this direction. So since I3 is entering R1 from the left, voltage polarity has a plus on the left, minus on the right. Since it's entering from the right for R2, it's plus here and minus here. And then plus here and minus here for I1. So again, R2 is shared between mesh 1 and 3. And so R2 has two voltage drops. And R1, of course, is not shared, only one voltage drop. If I apply KVL again in clockwise direction, I'm summing up voltages again from the bottom left corner. I have, what do I have? Plus VR1 minus VB plus VR2 due to I3 and minus VR2 due to I1 equal to 0. It's the shared branches that sometimes complicate things. But VR1 minus VB plus VR2 due to I3 and VR2 due to I1. Yeah, that's correct. All right, any questions? And again, I'll repeat, it does not matter which direction you choose for your mesh currents or which direction you choose to sum up the voltages by applying KVL. Yes.
On this one, VB is negative. Why would the VA in mesh one be negative?
So let's see, VA for mesh 1. Yes, that should be negative too. That's a good catch. That was from Friday. Voltages in a clockwise direction, minus VA plus VR2 I1 minus VR2 due to I3 plus I1 due to R3 and minus I2 times R3. So the point being made was, shouldn't VA also be negative in mesh 1? Which is absolutely right. Yes, VA also should be negative because I'm adding up voltages in a clockwise direction. So I'm adding up voltages in a clockwise direction. I encounter the minus sign first, so minus. See, tiny error like that, and my entire analysis, even though everything else is correct, my final answer would be incorrect. All right. Other questions? Does everybody understand the method? Okay. Once we have this, we again apply Ohm's law. And I can write VR1 is, of course, just I3 times R1 minus VB plus I3 and minus I1 times R2 equals 0. Assume mesh currents, write out the voltage drops, apply Ohm's law, and then you have your equations. Once you have your equations, you plug in all known values and solve. Unknown variables, which are the mesh current. Again, the whole purpose of these two techniques is so that we can solve for the unknown resistor and the unknown resistor, unknown resistor voltages and the resistor currents that are present in the circuit. The branch current assumptions for node voltage and the mesh current assumptions for the mesh current analysis, they are simply unknown variables for us to solve the circuit. And that's all. So setup of the problem is very important. Once you set it up correctly and you apply KVL or KCL correctly, your final answer should be correct. So when you're practicing homework, when you're practicing these problems at home, take your time. Okay, take your time. As you just saw, one small minus sign, an error in the first equation, even if everything else is correct, I will end up with the incorrect answers. All right, 10-second pause. Think over it. Let me know if you have any questions. Yes.
So when we find I for all these things, you said this was all hypothetical.
Mm-hmm.
Does that actually tell us the current that's flowing through R1?
Yes. So the question being asked is, how can we use the mesh currents to determine the voltages across the resistors and the currents, the actual currents flowing through R1, right? So let's say, I mean, we'll do an example where it'll make more sense, but let's say I1 was plus 5 amps, and then you found I3 to be minus 3 amps. As an example, I1 was plus 5 amps, I3 was minus 3 amps. So now we know the values for these hypothetical currents, not real currents. Which direction is the current actually flowing through the resistor R2?
The direction of I1.
Absolutely. So I1 is going this direction, I3 is going this direction. This is 5, this is 3. Both of them going in the opposite directions. So whichever has the higher value, that's the direction of the actual current. So my answer for IR2 would actually be 5 minus 3, which is 2 amps. Does that answer your question? And again, if I had chosen the opposite direction, for my assumptions, let's say I chose I3 to go counterclockwise, and I1 and I3 are both going in the exact same direction, then my values for these two would be different. Does that make sense? Right? Your answers, the magnitude as well as the signs for your answers all depend on the direction of the current that you choose. So if you choose a different direction from what someone else might choose, your answers will also be different. But when you solve for the actual branch current that is going through the resistor on the actual resistor voltages, they should end up being the same. Okay. All right. Okay, all right, so we'll end class here today and we'll pick up here again on Wednesday. Remember, mesh current was introduced last class on Friday. Hope some of you at least opened it up. We have covered the main theoretical explanation of mesh current analysis. So get started on the homework. There are 3 problems, and I will cover the example on Wednesday, and then the homework will be assigned perhaps Friday or Saturday next week. But again, do not wait while the lecture is still fresh in your minds. Go ahead and start working on the homework. Office hours this afternoon as usual. I'm also available for a few minutes after class.